The idea, one of the most important ideas I want you to walk away with, the life of a well is a path. It's a path. The scary news is that path is governed by what you and your company believe the worth of money is. All right? Because of that, what you do day one impacts whether there will even be a day two. I'll tell you a specific example. One of my clients retained me to evaluate their Haynesville prospect. I'm sure you're familiar with the Haynesville. The Haynesville stuff is over near Shreveport, Louisiana. It was considered to be just the shale play for gas. Unfortunately, it's come into some considerable disrepute. The reason for the disrepute is the fact that in the Haynesville, these wells would literally produce 50 million cubic feet a day. Prolific wells. The problem was the operators were more interested in showing high initial production rates than they were in showing reserves, EURs. So they were basically using an infinite value of money, 35% and up. They were producing the wells so hard, with so much pressure drawdown, that they were collapsing the fractures. The rock was actually flowing, believe it or not, the rock was actually flowing. They put so much pressure gradient on it that it would actually force the rock into plastic flow. And it would fill up the well bores. The wells would die, needless to say. Rock is not exactly a saleable commodity. The wells would die. I showed my client what they were doing wrong. They decided that they could not convince their field people to do business any other way than these extremely high pressure drawdowns. They actually sold the property because they didn't think they had the ability to convince their field people to manage the wells correctly. It's like, whatever. Well, that goes right to the heart of this question of the path. They were, within literally a couple of weeks, completely destroying the productivity of the well because of the way they managed it. Another operator that's an offset to that one did get the message, did realize that they had put too much drawdown on it, actually made a public release in their investor conference call, in their quarterly investor conference call, and their wells don't have the problem because they realize that pressure is not an issue. So this path idea really is a critical one. All right? One of the pieces of that, every well will be damaged as it ages. It's unavoidable. They will be damaged as they age. When they are damaged, we must find a way to remediate them. And I would put on the table for you, there are two major challenges. One is understand maturation processes, because I think once you understand maturation processes, how oil and gas are formed from the kerogens that exist in the rocks, once you understand those processes, you're going to discover that oil and gas are not a finite resource. I am absolutely convinced that we have already in place the technology to make oil and gas a renewable resource in its own right. We know how to do it. It's just that we haven't found the economic incentive to do it yet. But it's doable. The largest gas well in the state of Colorado is the landfill out by the airport. I'll tell you something. The second piece of the puzzle is we've got to learn how to do remediation in horizontal wells. We do not at this point have a technology that allows us to remediate damage to horizontals. So this path story really has a lot of pieces to it, not the least of which is the maturation, and the next piece is that remediation part. All right. Come on. Oh, it decided it doesn't like me again. And it's turned on, right? Wellbore storage. Wellbore storage for production data is not an issue because the thing that controls wellbore storage is the ease with which fluids can come into the well and or leave the well. In this case, the thing that controls the departure is that master valve, and the master valve is going to be big enough that we're sure that production can occur. So storage is an issue for us. The productivity index. My thesis to you is the productivity index is a measure of efficiency about how the system uses its energy. You say, well, we've always been taught pressure. I know, I taught pressure too. But the fact is, pressure is the measure of the amount of thermodynamic energy the system has in it. Right? That's a little different statement. We use pressure because you could actually use temperature. Temperature is actually a usable metric too. A couple of you came up and asked me about, well, why does the wellhead get cold? Well, it's Joule-Thomson cooling. Interestingly enough, many liquids, and oil is one of them, many liquids actually have a negative JT coefficient. Natural gas has a positive coefficient, so when natural gas expands, it gets colder. Many oils, actually, when they expand, get hotter, which is kind of weird. You stop thinking, oh, that's some strange thermal. Well, maybe that's what happens. But the productivity index, when you think of it in terms of its thermodynamic meaning, we use pressure as the measure of the amount of energy the system has in it. We use rate, in the productivity index, we use rate because it is the measure of the amount of stuff that is consuming energy. So with that idea in mind, the productivity index, or the reciprocal productivity index, is a measure of the efficiency with which the energy is used. Okay? So, with that idea in mind, I want to know how that energy is consumed. Under all of these assumptions, and we spent quite a bit of time yesterday wrestling with those assumptions and why virtually none of them are valid in the real world. I would bring back to your attention that the fact that these are invalid, that has nothing to do with it. Because what I want to do, where we're going to go here, is I want to see what the real data looks like. My model's nice, it's really cool, it gives me a skeleton around which to work, but that's not the core of the story. The core of the story is, what does the real data look like? And so that's why these graphs, we're going to pick them up here in a second. On this graph, which is a measure of efficiency versus time, the slope of the line tells us about the way the system changes its consumption of energy. Okay? The way the pressure changes over time. The primary tool for looking at that is the log of time, corrected for the amount of shut-ins that occur. All right, so a shut-in, the well produces, it gets more and more energy consumption, the well's shut in, and essentially it backtracks. The idea of superposition. The idea of what you look for in a Horner plot. We need to spend just a second talking about Horner plots. Then we put the well back on production, and it retraces that same path because the pressure transient moves through the same part of the reservoir. So that slope, a shallow slope, means that the well is very efficient in its use of energy. A steep slope means it's bad, high and low conductivity. The next piece of it is the overhead, which is basically the connectivity between the reservoir and the wellbore. Okay? But it's still a measure, but it says this piece of it is not time dependent. Well, that's not quite right because these systems are time dependent. That skin, that overhead, can and does change over time. Linear systems, we'll move on beyond that for now. Once you are in boundary dominated or pseudo-steady state, Barré and Cox wrote a really seminal paper about the fact that the appearance of boundary-dominated behavior can also be time-dependent skin, right? So we've got a little more to worry about than just simply the fact that it has gone into pseudo-steady state. For some reason, my machine decided to quit. So, anyway, the slope of the line, in exactly the same sense, the denominator there, equivalent time, is the Horner producing time, Q over Q. Exactly the same thing as you use to calculate T sub P when you do a Horner plot. So that Q over Q is the value that occurs at a point in time, the Q prior to that point in time divided by the rate at that point in time, and then you plot the RPI value opposite that. So that's simply a measure that permits you to calculate the pseudo-steady state pore volume. The boundary condition, the idea of sympathy, that the rate and pressure drawdown, when the pressure drawdown goes up, the rate has to go up, and vice versa. When they fail to do that, that's the onset of a new transient. Okay? So a new transient forms when that statement is violated. The idea of pseudo-pressure, pseudo-potential, whatever term you want to use, I use this simply because it's a way to permit me to understand multi-phase flow. All right? Gets me around some of the problems that Al-Husseini and Raimi came up with for oil and gases. But using that, I get you correct for the non-ideal fluid properties. the dimensionless pressure term. Dimensionless pressure is simply just that. We put this together because it had no units. And it really raises the idea, here's the reason RPI is plotted, because this is the term that arises in the dimensionless pressure group. In the dimensionless pressure group, it's a function of reservoir conductivity. Reservoir conductivity, we don't know what the thickness is, so we're kind of stuck. We've got a problem. We don't know thickness. So it's okay, because the slope of the line is just KH anyway. Then comes that monster dimensionless time. Dimensionless time is my analogy about the Porsche and the Suburban. It is simply a measure of the speed with which a pressure wave can move dependent on the amount of stuff in the system. And it really is an energy term in the same sense as the RPI value is, because the energy consumed with the motion divided by the energy that resides in the system. We talked about microseismic, move on beyond that. Then the equations, and those all look hideous, except they're all equations of straight lines. So the theory, for the very stylized real-world model, the theory says we should be looking for straight lines. So when we don't see them, it tells us something about the behavior of the system. Let's not worry about middle time. So my assertion to you is this approach permits me to understand the behavior of varying rates and varying pressures from which I can calculate the reservoir pressure, the reservoir conductivity, the apparent fracture rate, the pore volume, and how they change in time. Now that's quite a large statement compared to the claim that's made about Horner, basically a Horner analysis or shutting. So let's spend a second in that part of the swamp. I'll just leave that. School here. A Horner plot. When you do a Horner plot, because a bunch of you got some homework back yesterday that had Horner plots on it. When you do a Horner plot, what is the precondition for being able to plot a Horner plot? What did he say? What was that? What had to happen prior to you being able, you had to have a piece of graph paper or a computer, don't go there. In the well, what had to happen prior to you being able to collect the data that ultimately became your Horner plot? It had to be produced. Now, you said steady flow. Does it have to be steady flow? Huh?
There should be no flow.
How do you get it? Wait a minute. Careful. Real careful. A shut-in test implies, and here's where I'm going. A shut-in test implies that something had to be produced beforehand. Yes? It's impossible to have a shut-in. It's impossible to have a shut-in unless there was production that created the event of a shut-in. And you say, that's really stupid. I know it is stupid, but it's really fundamental. The very first time a well produces, that's the key issue. It produces. Because prior to that, it had never produced. It had never produced. You put it on production, it is never again going to be the same. The next event that we perform is this shut-in for the purpose of calculating a Horner plot. So I'm going to make this assertion to you. Perhaps the most important piece of a Horner plot is not the shut-in. It's the production that preceded the shut-in. Well, the way we handle that, we kind of cheat. We cheat on big time, in fact. When I look at a Horner plot, I have already had to admit to you that I had some production. Yep. I'm not going to have a shut-in unless I got production. So I have got some amount of cumulative production, right? And I don't know whether you went through the theory or not, but the existence of the cum production means that I created, if I'm looking at pressure and distance out into the reservoir, right? R is distance, radius, out into the reservoir. Units of radius are Those of you that ever worked with horses know what a hand is, right? Anybody in here never worked with a horse? Yeah, exactly. I got one. Actually, I got two of them. But that's approximately 5 inches. So we'll use some really funky units, eh? And pressure. Let's see. We can use pascals. They're cool. We could use kilograms per square centimeter. That'd be weird. Anyways, when I incurred this production, I created a pressure sink. As time passed, I created a pressure sink, right? So the pressure at the wellbore was dropping. And the pressure wave, just like my pebble in the lake, that pressure wave started moving out. And that's what I'm trying to show here. As it moved out further and further into the reservoir. And remember our conversation. This, our mental picture of this is that this thing is circular. And there's the well right precisely in the middle. Nah, I'll pull you back for a minute. That's not what happened. This thing is a sausage, and the well is never in the middle of the sausage. All right? Throw that other picture away. It's wrong. There's just so much compelling evidence from the geologic world. This is, well, see now, I just, how thick is my reservoir? How thick is my reservoir? Yeah, baloney. This thing is not a single plane. There's no such thing as a single plane reservoir. This reservoir from which I am producing and from which I intend to take a horn plot looks like a sausage. Actually, it is a Vienna sausage. No, it's a Oscar Mayer wiener. Oscar Mayer wiener. Could be. That's not an inconceivable shape. Or it's a good picture. The volume that we have tested with our production data is a volume, not this flat surface. Okay? So don't go there. We are doing a production test. We are creating a transient in a system which is irregular in the most extreme ways we could imagine. So I can imagine, I was trying to get you to have this little picture of a balloon. That's not a bad picture of this universe, because there's no such thing as a flat reservoir that's 2 inches thick or whatever. Okay? The pie pan model doesn't exist. There's no such thing. Anyway, the pressure wave, unfortunately, to draw the picture and to try to engage the idea, I need to introduce it with this much more simplistic model. The pressure wave has moved out. Okay? Now, I shut the well in. What happens? This gets a little bit confusing because when I shut the well in, let me draw this up the other way. I've had my pressure transient moving out, like so, yeah? That's how that pressure transient is moving as time passes. So these, I hate to use the word circles, these shapes here coincide with these lines here, all right? I'm trying to give you the top view and the side view, if you please. So I've been producing the well, the pressure has dropped. The pressure wave has also moved out into the reservoir in some kind of irregular fashion, but that's okay. Now, we turn the well off. I'm going to close the master valve. Have you ever noticed, you probably haven't been around the field enough, it's kind of fun. You'll wind up with a roustabout crew, and you'll see these guys, you talk about macho, that's what it's all about. These guys who are, they got muscles like Schwarzenegger used to have. It's invariable, they will have contests with themselves to see who can close the master valve with the least number of spins. These guys can, some of these guys are strong enough, they can actually spin and close the master valve in one throw. Do not get into an argument with them. Because they could drive you into the ground head first and they can do it. Well, there was Grafton. Anyway, we're going to shut the well in now. What happens? What happens? This pressure starts coming up, but at the same time, this guy continues to go out. The pressure wave I first started is still continuing to move out into the system, right? It's moving on outward. But what happens when I shut it in is I now have this well, the condition at the wellbore. If I were lucky enough to have a sand-based shutting device, the pressure starts to rise here, but it creates a new transient also. All right? And it's moving the same way. All right? So basically what I have is another transient that's a consequence of the shut-in that's moving outward also. Okay. That makes life kind of interesting. The way I want to handle this, transaction is the last rate at the shut-in. I'll call it piece of P, at the end of producing time. So that's going to be my T sub P value that goes into my T sub P plus delta T. The delta T is the amount of time since the start of shut-in. So that's corner time. That's just the classic data. Sometimes you do the derivation, you turn it over. Doesn't matter. It just changes the way the graph works. But the graph is basically the same story. So let's think about what's on that graph. This is the pressure as the well builds up, plotted against this idea of Horner time. And ideally, if the world was absolutely wonderful, all I would get is a straight line. It would be that simple. Ah, gosh, I could have my clerk do that. I could have my mother do it. Well, that's a different story. That's what would happen. The slope of the line, what's the slope of that line? What is the slope? It's the conductivity of the system, right? It is telling us, whereas when I look at production data, the slope of the line is telling me how the amount of energy that is used increases, right? Now I'm in shut-in, and I'm going the other direction. So the line is telling me how the system is recuperating, okay? So if I had a system which could recuperate fast, that would imply that that system had high conductivity, and therefore the slope of the line would be, oh, come on. I'm going to go get a sip of coffee while you think about it. If the slope of the line is steep, what do you calculate for KH? When you see the high KH, steep slope, that means that the system is recuperating very rapidly. That's the reverse. Because what I told you over here for production data, a steep slope is bad. Well, that's not wrong, because here I have just reversed the setting. Right? I'm talking about the well being shut in, recuperating. Over here, when I look at production data, it's the opposite. Therefore, the slope should be opposite. The sign has flipped over. Duh. Not a big deal. But, okay, so the slope of the line is predictive of KH, just like over there. The elevation of the line where do we measure the elevation of the line? Where is it that we measure the elevation of the line? Yeah, well, not really. This is usually plotted as a log, LN or LG, I don't care. 2.303. Most of my answers, if I get within 2.303 of the right answer, I'm really doing good anyway. So I don't care if it's log base 10 or base E or base 6. Hey, that'd be cool, wouldn't it? Whole new concept in residential well testing. We'll not plot log base 10 graphs. All jobs, all analysis from now on will be done with base 6 logs. How about that? And nobody in the world can figure out what you're doing. You're saying, no, I'm sorry, this analysis of the Horner plot was done with this really cool log base 6 analysis, and it gets a much better answer than your crappy log base 10 stuff. Yeah. Nobody will understand what you're doing. It's job security in the extreme, isn't it? I mean, it works. Works for me. Okay, anyway, all right, sorry, that was a sidetrack. Slope of the line is predictive of KH. Elevation of the line is predictive of how about it? I made myself notorious at mines for doing this. Now they're all late. That thing doesn't fly worth a crap. I need a heavy one. Okay. Well, yeah, no, it's true because the coffee wouldn't work because all the guys in between did stuff spilled. But it'd be a really great impact back about 2/3 of the way, wouldn't it? Okay, here we go. You ready? Okay, never mind. I'm sorry. Elevation of the line means what?
What do you mean by elevation?
How far up it gets from zero?
The initial energy of the system.
No. Be careful. There's two variables at the table, and don't confuse them. One of the variables is the skin, the connectivity between the reservoir and the wellbore. The other one is the P stop. All right. Unfortunately, those are coupled. I didn't make you mad by throwing something at you, did I?
No.
Okay. Well, you got to go back to reality. He was not one of them that was I was throwing things at. I just had to wake those guys up back there. I made myself very notorious at mines because we had, back in the day, we had the heavier felt erasers that, they weighed 6 or 8 ounces or something. And I got good enough I could hit somebody in the back row with one. And somebody back there sleeping or something, pew! So it helped a lot. Once in a while, just as happened here, they would come back to me. So if I was sleeping with my, I was writing on the board, whack! Turnabout's fair play. There's nothing wrong with that. Anyway, the elevation of the line. The actual elevation of the line. Y equals mx plus b. To calculate the b from this is a way to measure the skin, the effective or apparent fracture length, the connectivity between the wellbore and the reservoir. All right? So XF, or R sub W, RWE, okay, can be measured from that. Now, let's go back, go one more step here. I think this is appropriate conversation, not because of whatever you've been doing in the well testing class, but because this exactly ties with the ideas we've been wrestling with over here on production analysis. A real data set is going to look like this. It's going to be an S-curve. Invariably, I would say way less than 1 in 10 real data sets exhibit anything other than an S-curve. It is rare that some other shape forms because one of the major constraints of it is this discussion we had about storage. Storage is controlled by the conductivity of the reservoir, the ability of the fluids to get from the reservoir into the wellbore. So this early part, usually, but not always, it's the storage. All right? If you were to look at it on a log-log plot, it would create a slope of 1. If you look at it as a delta P plot, dP versus time, it'll generate a 45-degree slope. Storage has that signature, with one really important caveat. In gas wells, you are forcing the assumption that the temperature is constant. If this well, and in particular, why is this important? It is very common that an operator will use what they refer to as limited entry. Limited entry is the strategy in which you deliberately put very few perforations in the pipe. Limited entry causes very large pressure drops at the perforations during production. Because of the large pressure drops, a lot of Joule-Thomson cooling occurs. Because of Joule-Thomson cooling, the wellbore gets very cold. I mean, it's not uncommon. You know, people really have a problem with it. If you've ever done any business, or I hope you'll get to do it, Moomba Basin in Australia, Moomba Basin reservoir temperature is around 360 degrees F. Think about it, 360 degrees F reservoir temperature. What you do is the frac jobs, on the flow back of the frac job in that place, the frac job fluid comes back smelling like burnt sugar, because that's exactly what it is. The temperature is so high, the oxygen in the guar burns the gel, and it comes, I mean, to produce a well down there, it stinks to high heaven. It's not dangerous, but it smells of burnt food, because the temperature is so hot that it burns the fluids. So, the reason I tell you that point, once those wells are put on production, it is very common that the reservoir temperature, the 350, at the wellbore is now 30, 40 degrees F. 300 degrees drop because of the Joule-Thomson cooling. Those wells are not constant temperature. The storage does not exhibit a unit slope. It does not exhibit a 45-degree line. You say, well, that's down in Australia. Yeah, well, that's true. Except there are parts of the Ellenberger that are pushing 200, and I know that they are not constant temperature, isothermal. I know that the Ellenberger doesn't exhibit constant temperature. There's not a reservoir in the world that is truly constant temperature. So, to simply categorically expect a unit slope line is a little bit naive, all right? It just doesn't happen in the real world. Not because it's not theoretically correct, because it is, but it's based on the assumption that the temperature